Thanks for having me, everyone. Especially thanks to the organizers. It's quite a privilege to be able to talk here. I'm talking about implementing image filters in Go. You might have seen this talk also referred to as Instagram filters in Go. I would warn against that because you probably will get sued if you copy Instagram's filters. So rather make your own filters, but we're going to cover that as well. So a quick context as to who I am and why I'm talking about this. I work at a company called Over. We launched an iOS app about 5 years ago. It's design software. It's to help you do your own marketing and social media, that kind of stuff. And to get to market quickly, one of the things we did is we made a lot of use of the Swift, well, at that time it was Objective-C, but we used as much of the iOS framework as possible. Then fast forward to last year where we launched an Android app, and obviously we can't bring those technologies over into the Android space. So we kind of started from scratch and we had to reassess a lot of our rendering technologies and how do we write them in a platform agnostic manner. And then towards the end of this year, we're hopefully shipping a web app. And at the same time, I'm working on a headless rendering engine. So we've been looking at everything we're doing on iOS and kind of rethinking how do we do it across all these platforms. So you might be asking, what does this have to do with Go? Go is generally used in the cloud for like back-end engineering. So what does this have to do with pretty pictures? Well, we wanted a reference implementation first. So we're defining these algorithms or these kind of rendering pipelines, but we wanted a reference implementation so that we could compare the Swift, Kotlin, and TypeScript code to something else which we knew was correct. Go has been a great language for doing that for pretty much the same reasons you'd use Go for anything else. It's simple and very easy to read. That's particularly handy when you've got people who are Swift engineers and they need to read your implementation of an algorithm. And it's just simple code to read. Static binaries are fantastic because just as it's easy to deploy a binary to the cloud, it's easy to send one to another developer's machine. We have a private homebrew tab, and so anyone on the iOS or Android team can just brew install some Go tools and then run them themselves, and it works really well for us. The standard library is obviously fantastic. So we have very few dependencies. All the work I'm going to show you in this talk uses no external dependencies. So that's very easy in terms of portability because we've actually had the case where you can copy and paste Go code into like C or Kotlin, change the syntax, and it basically works. It's pretty fantastic. And then obviously portable. So one of the goals for this reference implementation for some of our rendering technology was that we actually wanted it to be able to run on commodity hardware. So as you see, my next point is about performance. Yeah, there's fancy GPU stuff we could do, there's fancy frameworks and things out there, but ultimately this should run on a very low-end laptop and in cloud functions or lambdas or whatever. This should just be able to run anywhere. And then performance, for us this was fast enough. The work we're doing here isn't part of a user interface, so it doesn't need to run at 60 FPS. All the other teams are doing that because they're actually, they have access to a GPU mostly. So this Go was fast enough for us. So quickly, I'd just like to touch on what an image filter actually is, just so we're all on the same page. I'm sure you've seen Instagram or Darkroom, Pixelmator, Photoshop, those kinds of things. These are very common examples of an image filter. However, these things are not image filters. These are what I call effects. So an image filter is just changing color. An effect is adding something to your picture, maybe a lens flare or some grain or a vignette. That's a different thing, and that's not what I'm going to be covering today. To put this in terms of an interface or some code that we can understand, you could say filter the interface as a single method apply, which takes an image and returns a new image, right? Sounds pretty simple, but we can actually be a little more specific than this and say a filter takes a color and returns a new color. Because filters don't need to know the size of your image or what type of image it is or the color profile, anything like that. All we're operating on is single colors. This also helps for concurrency as well. So there are two popular approaches. These have been hotly debated within the company I'm at now. The first is filters as config or presets. So this is just saying, this filter, it increases the saturation, maybe it adds a bit of fade. That's great, right? It's just simple and it's clear, but the problem is this. So these are some of the color adjustments you can do to images, and if you're taking this approach, every single client needs to know how to interpret every single one of those fields, and you obviously have different algorithms for each one. So that means you need to, every algorithm you could possibly want in a filter, you need to implement before you can actually use it. And then you also have to worry about rendering order, which filters come first, do they affect each other, all sorts of problems like that. So we actually decided against this approach. Although arguably this is probably the most pure and correct, we wanted to actually get something into production, so we didn't do it. So enter lookup tables. Lookup tables are what I'm going to be focusing on for the rest of this talk. Conceptually, all a lookup table is doing is taking an expensive, in terms of compute, or complicated calculation. You write down the inputs and you write down the outputs. That's all it's doing. So this started off back in the 60s when compute power was very expensive as literal books, where you would write down the results of expensive computation, and then you would go and look up the results. Okay, it's pretty simple. We haven't come much further than that right now. I put Redis here as well because you could actually think of any key value store as a lookup table. They obviously, there's more complexity in terms of expiring cache and that kind of thing. But essentially you're saying, take this expensive operation like a database query or maybe a network call to a third-party service, and use the inputs to just store the output somewhere else. And that's really quick and easy, and I can just go and use that instead. And then the other interesting reference I have here is bitmaps and vectors. So vector images, they're incredibly small to store because you're actually storing operations. You're saying this is a circle, and here are the control points, and it's this color. But that means the client needs to know exactly what a circle is, how to render it at every single resolution. And so it actually just defers the hard work to the client. Whereas a bitmap image is just saying, these are pixels. As long as you can render pixels, everything's cool. And you know nothing about shapes or objects. You just render a pixel. The great thing about lookup tables, firstly, they're just files. So that's cool. But it's pretty much a standard in the film world. So it's quite easy to just Google free lookup tables, and you can find them to copy the color profiles from the Matrix or the Lord of the Rings or whatever you want. These things are readily available online, and it's a very portable standard because they are just files at the end of the day. Some important components of a lookup table. There's the size, the domain min and max, and the data points. So these are pretty self-explanatory, but you'll see them being expressed in different ways. The domain min and max is describing the data points and saying what they essentially, maybe they go from 0 to 1 or 0 to 255. And the size is just saying how many points there are. So it's pretty simple. But this brings us to the first example of a lookup table. So this is an image LUT, as we also call them, one of those nice acronyms. This is a neutral LUT. So if you actually try and apply this to an image, the output will be exactly the same as the input. And so that just gives you, it looks weird, but you actually start to get used to them. So these are usually 512 pixels square. They can be created in any image editor, which is really nice. So in principle, you can take that image, put it in Photoshop, do a bunch of stuff to the color, export it as a PNG, and use it. So very portable. They can be inspected visually, so you can actually look at it and kind of get a sense of what it's doing. You'll see in the next slide what that looks like. But there are problems with it. And the one is that you need to actually look at it and assess some of those attributes I mentioned earlier. What is the size of this LUT? You have to go and count the cells in that grid to actually figure it out, right? What's the domain min and max? That depends on the image type. Is it a 48-bit image? Is it a 24-bit image? You have to actually go and figure these things out. And then because they're images, you need to be very careful of compression. Image editors are very keen to compress your images. but because this isn't actually an image, it's actually a data store, we don't want to compress things. And then you have all these other variables like color profiles and bit depth, which you actually ran into now, because Android can't load 48-bit images, but they can load 24-bit images, and Photoshop might sometimes just give you higher bit depths. You don't know. These are some examples of image LUTs. So you can actually kind of see what these filters are doing. There's some grayscale filters. Some of them are a bit faded. You can see some of them have quite harsh contrast. And it's actually really great being able to look at them like this. In terms of actual code, so I'm not going to go through boilerplate of opening images and looping through the pixels and that kind of stuff. But the interesting thing here is what you need to do for each input pixel is actually convert those RGB values to XY coordinates in this image. And the way you do that is the blue value actually maps to the cell in the grid, and then the red and green values map to the X and Ys within that cell. So the first thing you need to do is convert your input domains, so that's probably 8-bit color channels, which are 0 to 255. You need to map them to whatever your domain min and max are, which is, I think here it's 64, or yeah, 64. And then you just need to do the calculations to figure out what's the XY value here, pull that pixel, and that's your output pixel. This is one of the easier implementations, and it's working pretty well for us. The other format for a lookup table that we can use to do these color filters is called a cube file. This is what it looks like. It's just a ton of numbers and a little bit of metadata. The nice thing about these is that there's a spec, which was written by Adobe back in the day, and pretty much everyone sticks to the spec. So that's actually really handy. You can open it up in a text file and just look at the values, as opposed to images where you need to open them up in Photoshop or something to actually inspect the pixel values. All the metadata, so domain min and max, the size, even a title or whatever, all those things are just written in plain text. So you can just go and pull that out. But one of the downsides is that they can't be inspected visually. So you can open it up and look at the numbers, but you have no idea, is this doing grayscale or high saturation? You have no idea, which is, I think it's a decent trade-off. Nice thing about having a spec is you also have a reference implementation. So that, I don't know what to call it. Call it an algorithm, I guess. Comes straight from the spec. Here, instead of looking for XY coordinates in an image, you're looking for the index within all those values. So, you could think a line number, essentially. The difficulty is that they don't specify what types the numbers are when they talk about them. So they talk about the red value, and you don't know if that's 0 to 1, a 64-bit floating point, or if it's an unsigned 8-bit integer, which is 0 to 255. You have no idea. So it took a while to actually figure out how to get those values correct. But in principle, this works, and it's great. So you actually have two formats now, which are just files, and you can easily implement both. And great, so you've got a source image and a filtered image, and you think you're good until I've exaggerated it here. You see that there's a bit of banding on those images. And what was once quite smooth, like sky and, I don't know, maybe sand or something, now just looks like rainbows. So that's not fantastic when you're trying to ship, a professional image editing app. So this brings us to color resolution. If you're using a 24-bit image, you've got 16 million colors, essentially. And these lookup tables have about 260,000 colors in them. So you're losing millions of colors, and that's a big problem. Enter interpolation. I had been a user of interpolation before, but never actually implemented it myself. It's a very simple concept, and any data scientists or mathematicians are probably laughing right now, but I found it very fascinating. It is essentially saying, if you have a two-dimensional grid like this, and you have some known points on it, how do you get the value of unknown points? So you're drawing a line, and this would be linear interpolation, where you would just guess, well, not guess, but like use the two nearest points to figure out a point in the middle. So that's what we're going to do. We're going to take these 260,000 colors and turn them into millions of colors. There's a very cool library called Piecewise Linear, which was extracted from another project written in Go, which gives you two-dimensional linear interpolation. And I've put it here because it's a very cool library to play around with and just get a sense of how interpolation actually works and what you can do with it. So again, you'll see there you've got your domain values, you've got to know the actual size of your grid, and then you give it the X and Y values, and then you can just pull anything out of it. And it's, the first time you do it, it's quite magical. The problem is we're working in a three-dimensional space here. We're not doing two-dimensional interpolation. So you can think of your red, green, blue values as X, Y, and Z. And so you need to find a point somewhere in that cube. So it's not quite as simple. This gives you kind of a better mental model of how you can think about it, where 1, 1, 1 is white, 0, 0, 0 is black, and you now need to find values somewhere in between there. And this actually brings us to quite a nice natural abstraction called the color cube, which if you're working in a more graphical space, so you're on iOS or Android, you probably have this kind of abstraction baked in with frameworks. But in Go, I couldn't really find anything like this. So I invented it. So you've got a simple struct. It's got a size. It's got data, which is a three-dimensional map. And then you've got domain, min, and max. And you can see how the cube file pretty much maps one-to-one to this struct. The nice thing is you can also map those image lookup tables into this as well, with a little bit of trickery. There are three methods on this cube. You can just create a new one, which actually instantiates that map, which was quite a fun thing to do. And then you've got get and set, which is just X, Y, Z, which, get a point or set a point in the color cube. At this point, if you're interested in this kind of thing, I would highly recommend this book, Computational Color Technology, by Henry R. Kang. It was published in 2006, so it's actually quite old, but it documents a lot of these algorithms, and they are actually very fundamental to computer graphics now. So a lot of it seems quite basic, and it probably is available in many OpenGL libraries or that kind of thing. But if you want to know how to do it yourself, I would recommend this book. This is some of the kind of matrix math involved in doing three-dimensional linear interpolation, which you can also call trilinear interpolation. We scratched our heads a lot looking at this book and implementing these algorithms, but we managed to get something working at the end of the day. So in hindsight, it was worth it because we now understand these algorithms, and although the actual implementations might just run on a server and not necessarily in the apps that we ship, it's great because now we have such an intimate knowledge of these things. So this is cool, right? You've got really smooth images now. You can support these two different formats. You can render anywhere. It's fantastic. Until you let someone else brew install that binary and they start testing it with other things. And this is my last point, but transparent images completely broke here. And this perplexed me because I wasn't touching alpha channels in images. I would just copying them from one image to another. So I had no idea what was going on here. You can see in these two images, it was supposed to look like the one on the left, ended up looking like the one on the right. You probably can't see anything in the projectors. It's a very subtle difference. But they were wrong, and any changes I did, they would fix the transparent images and then break images that didn't have transparency, and that was weird. So I scratched my head a lot. Turns out the lovely interfaces that we have in the standard library sometimes hide complexity from us, which is actually quite important. So the color interface, it returns alpha pre-multiplied values when you try and get the red, green, and blue values from them, which means if the alpha channel is not 1, then they're basically multiplying them together. So this means that your values are actually going to be incorrect sometimes, depending on your output color space. If you're loading a JPEG or if you're loading a PNG, basically your results are going to differ. So what you have to do here instead is convert, well, I'm doing every pixel. There's probably a better way of doing this. But you set your target color model And then you just have to convert every pixel to that color model. That color model would be the same one as the image that you're actually going to write at the end of this process. So that fixed that. And then at the end of the day, we actually have a valid rendering engine now that can do these filters. I stole some concurrency code from, I forget the name of the library, but there's a lot of image libraries on GitHub that do basic contrast, saturation, those kinds of things in Go. So I stole that code, so technically it's not a dependency. And yeah, now we're using this, and it's actually been referenced to, this Go reference implementation is now actually being used. It was converted to RenderScript, which is kind of a subset of Kotlin as far as I know. It's like lower level. And then it's also being used in TypeScript as well, except there they're doing OpenGL and they can do 60 FPS. So it's actually working incredibly well. That's it. That's the end of my talk. Again, that's me. That's over. We have a cool app. You should go check it out. I will be open sourcing this code at some point. It's just kind of tied up with a lot of business logic right now. But hopefully, if you need to do trilinear interpolation in Go, you won't need to write it yourself. So yeah, thank you. Should we do questions?
Yeah, can do. Yeah. We'll try and do questions.
That's off. Sorry.
Turn that on again. We'll try and do some questions if we just get the other mic.
No, thank you
for that one. Any questions? I'll just go straight to the back.
It might be slightly out of scope of what you're talking about. You know when you see those old black and white images that people have colorized, is that using similar techniques to the ones you've described, or is it an entirely different deal?
It's different because what you're doing there is you're actually adding information. So you're taking, there's essentially one color channel instead of 3, and you could think of it as you're adding 2 more color channels. So it's a similar kind of domain space in that you are manipulating color, but you actually need to know a lot more about, you need to understand the image. You can't just say, given this pixel, make it this other pixel. So that's where ML comes a lot more into play, where you could even be doing object detection and saying, these objects are different, so color them differently. So there's a lot more kind of semantics involved, and it's often just done by hand as well. But in terms of actual code, you would have very similar input image, output image. It's just the secret sauce in the middle that would be different.
Any other questions?
Hi, great talk, thank you. You mentioned that you had done this transformation concurrently, and my immediate thought is that you spin up a code per pixel. But I also realized that that kind of thing might lead to kind of memory errors and things. So what kind of limit do you put on the number of codes you're parallelizing it?
So I'm splitting the image by line, so essentially by height. So for each row of pixels, I would spin up a Go routine, and it would process each pixel in that row. You can also do, well, I just call them chunks, so you could just split it into a grid, and you could define as many as you want. It kind of comes down to memory versus CPU and what your actual performance needs are. Obviously on a GPU, you could just, each pixel is its own, little coroutine. And that's how you can get that performance. But you also do sometimes lose a bit of accuracy there as well. So for example, in our web application, what we're probably doing, we have a WebGL implementation of this, which is 60 FPS. But we also need a fallback in case the browser doesn't support that. So then we can just go to this CPU. We could also disable interpolation there, because that takes up a lot more CPU power. But then on export, we would switch to the high-res CPU implementation, which might take longer, but gives you the most consistent and best results. If that answers your question.
Yeah. Any other questions? Okay, we'll take one more, and then you can follow up with Wayne at the break. But I mentioned if you had the hand up here, so there is.
Thanks for the talk. Do you work with raw format? Do you try to work with raw format?
We do not. And that is a decision that we've made just to limit the scope here. So I know on iOS at least they store photos natively as HEIC now, which is a much higher dynamic range. So there, yeah, the complexity is you're going from 0 to 1 to now maybe -2 to +2, or much bigger range. So that is possible, but most of the specs and standards out there don't support that. And also realistically, for what we're doing, we're targeting people who want to share on social media, that kind of stuff. You don't need HDR or OpenEXR or any of those more film-oriented formats.
Wayne, thank you very much indeed.
Cool.